Good morning, everybody. Welcome back. It's time to put everything together. And what do I mean by everything? I mean electric field and magnetic field. Because at this point, we've learned two forces, haven't we? The most recent one was the magnetic force. That was a charge, a velocity, and a magnetic field all interacting with each other that blew up into these right-hand rules. So basically, any charge that's moving in a magnetic field is going to feel a force. And we're going to investigate the implications of that. But we can't ignore what we learned in chapter whatever it was. 22? Did we start in 21? I don't remember these chapters anymore. Remember electric field? Yeah, I don't want to, Mr. Balogh, right? Okay, but now you're bringing that back? Yes, we're bringing it back, right? Electric fields. Electric fields exert forces on charges. Now, let's just review a little bit about what we know about electric fields and forces. The charges that go in here, the test charge, is always assumed to be what sign? Positive. We define everything with respect to a positive charge. So what is this equation over here on the right telling me? Let's look at direction. The direction of the force on a positive charge is equal to what? The direction of the electric field. So if I have an electric field that's pointing to the right, and I drop a positive charge in there, what direction will the force be? To the right. The electric force follows the direction of the electric field for a positive charge. What happens if this thing's a negative charge? It goes the opposite direction. So you think about it all in terms of positive charges, and then if it's negative, you reverse it. So that's just a very brief review of how charges experience force from electric field. Okay, over here for the magnetic, it's a little bit dicier, right? So first of all, do all charges experience force from a magnetic field? No, why not? What do they need? They need speed, right? They have to be moving in order to experience this force. If a charge is sitting still and there's a magnetic field there, there's going to be no magnetic force. Okay. We need field and we need force. Is the magnetic force on a moving charge the same direction as the magnetic field? Is this force direction the same direction as this magnetic field? No. In fact, it's horrible, right? Because the direction of that force depends on a cross product between the direction of the velocity, what the field is doing, right? And then you get a force that's perpendicular to both the velocity and the magnetic field. So we get zero from the magnetic force by either not moving, or what's the other way we can get zero out of a cross product? When they're parallel, when like velocity and magnetic field are pointing in the same direction or 180 degrees from each other, then we'll get zero. So a charge could be moving and experience no magnetic force if its velocity is in the same or anti-parallel direction to the magnetic field. They are distinct forces caused by different physical effects. However, a single charge can experience them both. So the sum of forces acting on a charge would be written as the force due to an electric field, Q times the electric field, plus Q times V cross B. The thing in the box is called the Lorentz force law. It is really the first equation that you are encountering in this course that is hinting at a deeper unification of electric and magnetic fields. Electric and magnetic fields are distinct things physically in our universe, but it hints at this idea that you really don't have just one or the other. You often have both. And spoiler alert, in 2 chapters, you're going to find out just how intertwined electric and magnetic fields really are. Okay? So we're moving in that direction, but we do have to consider all the things that could be happening to a charge and why it would experience force. We did one whole unit on basically developing the idea of the electric field. Now we're in the unit with magnetic field, but we don't want to isolate it to just magnetic fields. It's going to feel like that a lot, but we always have to keep in mind that there's an electric field lurking, more than likely, somewhere. So let's apply this, right? Let's apply this in the context of everything that we could do and know. Let's invent a mass spectrometer, and then we'll talk about Hall effect in apparently joysticks nowadays, because that's what's all popular. All right, so I'm gonna drop a magnetic field on the screen. Let's say that we've got a magnetic field pointed into the screen, sort of like in this zone, okay? And I'm going to take a particle. We'll do it in blue. And this particle is going to enter, like it's coming in right at the edge. So it's been traveling straight where there's no magnetic field. And now it's going to enter into this zone where I've got magnetic field pointed into the page. What direction will the force be on that particle as it enters the field? How do we find that? We have to use a right-hand rule. Everybody get your right hands out. You can't practice this enough. I keep forgetting to go find the right-hand rule practice website. Darn it. Somebody email me, because I keep forgetting. I remember in class, and then as soon as I leave class, I forget. Shake in the direction of V, right? Rotate wrist around until our fingers can do their 90-degree angle in the direction of the magnetic field, and our thumb points which way? Up. So that particle initially is going to feel an upwards force. Up to this point, we haven't really talked about what happens after. This particle's moving. It's been moving along, and now all of a sudden it gets a force directed upwards. What's going to happen to the trajectory? What's going to happen to the direction of the velocity? It's going to start pointing up a little bit, right? It's being pushed up, so it's going to start pointing up. So maybe a little time later, the velocity looks like that. Okay. Now that it's moving in that direction, what direction is the force? Is it straight up anymore? So again, right-hand rule. Shake in the direction. Now we're kind of going up at this angle, right? Fingers are still into the screen, but my thumb now, the force, is the force going to be perpendicular to velocity? Yes. Is it going to be perpendicular to the magnetic field? Yes, it has to be perpendicular to both, right? So there's the direction of mutual perpendicularity. I don't know if that's a word, okay? But you get the idea. Okay, so you got something that's moving along like this, and it gets shoved. So what happens to its trajectory? It changes, right? And sometime later, maybe its velocity is like that. It's not supposed to be slowing down. I'm just not drawing my vectors long enough. Okay, now what direction is the force? It's to the left, isn't it? Which pushes it again. So maybe it's like this, which means that force is now going to be pointing kind of down like that. This force direction is constantly changing because the force is causing the direction of the velocity to change. However, that force points in only one direction. What direction? What's a word for all of those red arrows and the direction they are pointing? Centripetal. In, towards the center. No matter where I start my hand, my fingers are into the screen. No matter where that velocity is, which way is my thumb always going to be pointing? Towards the center. The path of this particle is an arc. That was a really bad arc. It's an arc. Particles can enter fields and then begin to circulate within those fields. And they'll just end up circulating and circulating and circulating around magnetic field lines and get trapped. This is exactly where the aurora borealis and the aurora australis come from. What's the aurora borealis? It's the northern lights. It's when charged particles from the sun interact with the Earth's atmosphere. I actually, for the first time, went out and saw the aurora borealis last week. We had a geomagnetic storm, and there was enough charged particles coming far enough down from the north that I caught it on camera. Okay, I couldn't really see it with my naked eye, but my cell phone camera was able to see it. The red glow in the sky. I also saw the comet last week too. But these charged particles coming from the sun hit the Earth's magnetic field. And what do they start to do? They circulate. They have momentum usually along the axis of along the magnetic field. So they'll get trapped along those magnetic fields and they'll circulate and they'll get funneled into the Earth's south pole. Where's the Earth's south pole? It's where Santa Claus lives, right? Geographic North Pole is the Earth's south magnetic pole. And as those charged particles, helium ions, hydrogen, electrons, protons, come barreling in, they strike the Earth's atmosphere, the gases in the Earth's atmosphere, and cause them to emit light. And some of that light's in the visible spectrum, and you get these sheets of green and red floating through the sky. So that's where the positive things go. Where did the negative things go? If the positive ones go to the South Pole, where do the negative ones? They go, and that's where you get the aurora australis. So the aurora borealis, northern lights. Aurora australis, southern lights. My physics teacher in community college did her PhD thesis on studying the simultaneous aurora borealis and aurora australis and showed that when the northern lights are happening, an almost mirror image is happening at the southern pole. Pretty cool. Anyway. Why are we here doing this? This is a cyclotron. This is a device where we can actually cause charges to circulate and thus speed them up and make charges go really fast. So the inverse of sending something in with speed and getting it to circulate would be to get something to circulate to get it to speed up. Now, how do we go about doing that? Well, let's lay out kind of what's going on here, right? We have forces that are pointing towards the center of a circular motion. So let's get a circle on the screen. We'll get a nice clean circle here. Woot! I love cheating. All right. And then we have this magnetic force, which is pointing towards the center. The charge does have a mass. Proton, electron, doesn't matter. It's got mass. It's got charge. Could we apply some fundamental laws about forces here? I mean, we could. I know you don't want to. But I have to ask you to remember something. Do you remember Newton's second law? F equals ma? Yeah, not really. It's ma equals F. Okay, so how many forces are we talking about here? If we add up all these forces, how many forces are acting on that charged particle as it circulates in this magnetic field? Just one. The magnetic force pointing towards the center, right? And then, oh, this is really dusting off stuff. Do you remember what the relationship was between centripetal acceleration and velocity? Oh, that was good. Good job. V squared over R. Boy, this is like reaching back, isn't it? Okay, this force over here is Q times V times B. What the heck, Mr. Balogh? What happened to the cross products? Notice I've dropped some vector signs off here, right? Because I know that the magnetic force is pointing towards the center of this circle. I know the centripetal acceleration points towards the center of the circle. So if I call towards the center positive, there goes my vectors. Where did QVB come from? A cross product, Q times V cross B, can be written as QVB sine theta. Well, what's the angle between the velocity and the magnetic field here? It's 90 degrees, right? Because the velocity will be tangential. So the sine theta is sine of 90, which is sine of 1. Okay. Is there something I can clean up here? One of those V's can go away, right? And then I can multiply both sides by R to get rid of the R. Well, at least move it over to the other side. And then divide by QB. So what am I left with? I'm left with mv over qb is equal to r. Or in other words, just to write it the other way around, the radius that a charged particle will take in a magnetic field depends on what? The mass of the particle. So what is going to have a bigger radius, a proton or an electron in a magnetic field? For the same speed and everything, right? It would have a bigger radius because it has a bigger mass. There's like more inertia for it to fight against, right? Whereas an electron would have a tight circle. Is the charge on the electron and the proton the same? Say that again, Apple, but the other way. Yes. The magnitude of the charge is the same. But this is a magnitude equation, isn't it? Right? Magnetic field, charge, speed. So for a given speed, electron and proton moving at the same speed, having the same magnitude charge and the same magnetic field, the proton will circulate more. You have some pretty intense, devilish conceptual questions on this homework. And it's like overwhelming because one of them shows you a bunch of velocity vectors, another one shows you a bunch of arcs and circles in a magnetic field, okay? Those problems are tough because you're being required to kind of hold several pieces of information in your brain at the same time, okay? I've showed you the combination electric field and magnetic field Lorentz law. That's what the vector conceptual question is about. And then you got the one with the arcs, which is the magnetic. This circulation equation right here is what's going to help you there, right? But that radius is going to be determined by all of those factors. All right. How do we use this to make charges go fast? And why would we want charges to go fast? So pictured up on top are two real cyclotrons. The one on the left, you can see for scale, there's like a ruler in the picture, right? So that one's about, a little less than a foot across kind of thing, right? Do you see how there's a gap between the two semicircles? More on that in a second. The picture on the right, those are people standing in front of a cyclotron that was built at Lawrence Livermore National Labs. Lawrence is in there somewhere, Nobel Prize winner guy, okay? So cyclotrons come in all shapes and sizes, okay? Big, small, medium, all that kind of stuff. The bottom picture is a schematic diagram of how we can speed up a charge. That gap between the two semicircular magnetic plates has an electric field in it. So if we take like this semicircle, right, and we inject, stop pointing with my finger, right? We start a particle in here. Like if I do sort of a, let's do a top-down view. It's going to be bad. So there's one side. There's the other. There's magnetic field in here. Okay? And then there's electric field in here. Okay? If we start a charge, say right there, it'll curve until it gets to here where it leaves the field. And when it leaves the field, what direction will it go? What will inertia do? Just make it go straight, right? But now it's in an electric field. And the charge will follow the electric field, and it'll experience the force, so it speeds up across the gap. And then it circulates, and then it speeds up. And actually, I did that wrong. Starts at the center, speeds up, gets bigger, bigger, speeds up across every gap. It gets more and more speed. And so a particle starting in the middle will get sort of flung outwards till it reaches the outer edge. And when it finally leaves the magnetic field, that charge can be going pretty darn fast. Cyclotrons can get electrons up to 99.999 times the speed of light, depending on how big they are, how big their magnetic fields are, and all that kind of stuff. Why would anyone want to get an electron going that fast? Okay. The Large Hadron Collider is a synchrotron on steroids, but it doesn't work this way. Okay? It does have magnets. Those are steering magnets. That's a different thing. We talk about that in particle physics. There is a cyclotron very near you. It's not a hint. I don't think it's in this building. Every hospital, every major hospital, has one in its basement. Why? Generator? No, generators are much easier than cyclotrons. So MRIs, the M in an MRI stands for what? Magnetic. R, resonance. I, imaging. MRIs didn't used to be called MRIs. They used to be called NMRIs. What did the N stand for? Nuclear. What happens as soon as you start throwing around the word nuclear and human beings? They get scared. So you take the nuclear off. It's an MRI. An MRI does not need a cyclotron to work. It needs big magnets, it's true. But it doesn't need a cyclotron. Why would every hospital, every major hospital, have a cyclotron in it? MRIs, X-rays, other medical diagnostics, other technologies that make it so that we don't have to cut you open and let the demons out. Okay? Function on a principle where they've got to be able to take a picture of something. And sometimes you're trying to image soft tissue, like maybe stomach, intestines, something like that. And an X-ray just isn't going to pick that up, is it? Because an X-ray will bounce off the bones, the fluoride and calcium in bones, but it won't bounce off squishy bits. So you can give the patient something to drink. That does light up on an X-ray. And what lights up on an X-ray? Radiation. Barium. What is it? Right? It's like, there we go. Jeez. I was looking for BA. Why was I looking for it? Right? Okay. That's boron. 56. Thank you. I knew it was over here somewhere. Okay. I just couldn't see it. Barium has an isotope that works. Iodine's another one that's got an isotope that works. These are radioactive particles. that have very short half-lives, which means that they don't last very long, which is both good and bad news. So, Mr. Balogh, I had to have my GI tract x-rayed long ago to figure out what was going on with me. Spoiler alert, I have one. And so I had to drink a cocktail of radioactive goo, basically, okay? And it was so hilarious because the technician was like, so what flavor do you want? I knew it was in it. And I was like, there's flavors? He's like, yeah, there's strawberry and pineapple and chocolate. I was like, does it matter? He's like, no, it doesn't, but what flavor do you want? It's like, whatever. Whatever one you had the most of. I think it was pineapple. Anyway, it tastes awful. It just tastes awful. And you got to chug it, and then you got to do this dance to get it to coat all your insides. And then they take pictures. The good news is that you only stay radioactive for about like 10, 15 minutes. The bad news is that in order to make that stuff radioactive, if it goes away after 15 minutes, where do they need to make it? On site. How do you make things radioactive? Well, one way is to take very fast charges and slam them into atoms, knocking off neutrons and things, right, in the nucleus so that they become unstable and they turn into these isotopes that have great medical benefit. So cyclotrons exist. They're all over the place. If it's a lab that makes radioactive things for medical diagnostics, there's a cyclotron in there. Okay, because it's the easiest, cheapest, fastest way to get particles to go fast and slam them into other things. So that's like one application. But now we need to talk about mass spectrometers, because here's another application of getting charges to do our bidding based on how we can apply force to them. So a mass spectrometer, okay, so that's what they look like for realsies. But I'm going to draw a schematic of it. This is like an outline of how it works. A mass spectrometer consists of two parts, a velocity selector and then the measurement end. So to scale, sort of, this is what we're going to do. So let's say that we've got a mass spectrometer container that might look like something like, again, this is not exactly how they're put together. And we're going to have a magnetic field pointed out of the screen inside of this chamber, okay, where we're going to measure. Okay, back up. Mass spectroscopy. What is spectroscopy? What does that word mean? Spectrum of something, right? Okay. So spectroscopy is a part of measurement science where you find out the component parts of something. So a spectrum of light. If you look at white light, it has a rainbow spectrum. You would do spectroscopy to measure the individual wavelengths that are in your white light. Okay? So mass spectroscopy, what are we dividing up? Mass. We're trying to get a mass spectrum, okay? So for fundamental, easy little elements on the periodic table, this isn't very interesting. But when you get to molecules, okay? Molecules are made up of all these little tiny atoms. And let's say you're in a lab and you get sent this white powder that the person swears is just baking soda, right? Can you figure out its individual atomic structure and parts and thus determine whether it's baking soda or some other white powder? Yes, you can. Every molecule has a fingerprint. So we're going to figure out how to get the fingerprint. So this device, this big D-shaped thing, is like a measurement chamber where we're going to actually figure out what the masses are. But before we get there, we have to use something called a velocity selector. And it's this little tiny thing that I've drawn up here. I'm going to draw it bigger over here. Okay? So this is like a magnified version of the velocity selector. So our velocity selector, I never have a picture of this, do I? Of course not. Why would a picture be any good? A velocity selector consists of electric and magnetic fields at very specific directions that would make sure that the speed of our charges is exactly the same for every charge. Let me show you what I mean by this. So what we want is we want a charge to move down this velocity selector in a straight line. If a charge is moving in a straight line, what do we know about the net force on it? It's 0, right? It can't be accelerating, because if it were accelerating, it would be changing its direction, right? So in a velocity selector, we've got two fields we can play with. We can have a magnetic field and an electric field. And let's say the force from the electric field was acting down. We would therefore need a force from the magnetic field acting up to counteract it, right? So how do we get an electric force acting down? We charge the walls of the velocity selector. So what would the charge be on the top plate of my velocity selector here in order for the force to be downwards? I need positive up here and negative down here. Which way is the electric field going to be pointing? Positive, negative, is pointing down, isn't it? Which means the electric force will be down. Okay. Which way would I need a magnetic field in the velocity selector in order for the magnetic force to be up? Well, I know my V is to the right. I want my force to be up. So which way does the magnetic field need to point? Into the screen. So I get a magnetic field like this in here. And if the electric force and the magnetic force are equal in magnitude, we've solved the opposite in direction, but if those are equal magnitude forces, then this particle will travel through this velocity selector in a straight line. Well, we know what the electric force is. It's the charge times the electric field. We also know what the magnitude of the force is for the magnetic force. Crazily enough, what cancels? The charge. That's kind of handy, because it doesn't matter if what we put in there is singly ionized, doubly ionized, triple, right? The amount of charge on it doesn't matter. It does need to be charged, because if it's not charged, is it going to experience any forces? No. So we got to make sure that the sample gets ionized. And there's a part before the velocity selector where you input your sample and the machine just blasts it, okay, strips it, gets it ionized and bombards it with electrons. There's lots of different ways to get ions to form. And then it scoops that up and boom, sends them into the velocity selector. You're going to have all kinds of velocities going through the velocity selector. You'll have velocities that are really big, really small. They'll be kind of all over the place. But the velocity that is equal to the magnitude of the electric field divided by the magnitude of the magnetic. I mean, who knew that a Newton per coulomb divided by a Tesla is a meter per second? Really, just give up on units, okay? But if we hit this speed in the velocity selector, this will be the speed that causes particles to move straight through. If a particle is going faster than that, which way is it going to curve? What force wins based on how fast it's going? Magnetic. Magnetic is QVB, right? So if we are faster than this speed, the magnetic field wins. And which way is it going to go? It'll curve upwards. It'll do that if it's going too fast. If it's going too slow, who wins? The electric field wins. And it'll curve and slam into the bottom plate. Only ions that are moving at this speed can get straight through. So this is why it's a velocity selector. It doesn't give velocity to these things. It just, if the velocity isn't that, then those velocities will get removed. It selects the one velocity that lets them come through in a straight line, which is advantageous because now we know exactly how fast these little chunks of white powder are going. They're not chunks, they're atoms. Okay? And those get injected into the measurement area. So now we know the speed that these things are going. And we also know, based on our cyclotron results over here, we know the radius. And if we know, so there's two different B's here. We should be pretty careful. I'll call this one B prime. It's the one that's inside the measurement area. The curvature of these charges are going to depend on their charge, whether it's single, doubly, or triply ionized. It actually turns out to be fairly easy to distinguish for the machine. But really, the thing that's going to determine, because the velocity is all the same, isn't it? The velocity selector made it so that all the velocities are the same. Charges can be single, doubly, triply ionized. We know the magnetic field in here. The radius is going to depend on the mass of the particle. The bigger the mass, the bigger the radius. And so what you do is you put like a sensor along this side that measures the distance. It measures the radius of wherever these things are hitting. And the mass of the particle will directly correlate to the radius of its curvature in that secondary magnetic field. And we can distinguish between the different masses in the sample. This is kind of what it looks like, the outputs. Okay, some of you are recognizing this, okay, right? There's an intensity, like how much of it are you getting? Like how many hits are you getting for a given, and then this is a mass divided by the number of protons. Z in chemistry, that's it's atomic number, isn't it? Something mass number, something like that, okay? Right? It's a ratio. Again, it's easier to deal with the charges separately, and this ratio is good enough to be able to tell what's going on here, right? So here's the fingerprint for glucose. What's glucose? Sugar, main component in most kinds of sugar, okay? So, or at least the main sugar that we tend to use in a lot of our products. So that white powder, right, would have that fingerprint, okay? The fingerprint for cocaine, different, isn't it? There's glucose. There's cocaine. You can figure out what kind of white powder it is, right? Get a sample, run it through the mass spec, and the fingerprint will jump out, okay? Now, those of you that have used a mass spectrometer know that I'm kind of making it sound easy, right? Because you got to argue with that machine a lot. Okay, calibrations, there's all kinds of stuff you got to know about how to use a mass spectrometer proficiently, okay? But that's how a mass spectrometer works. So it depends on the kind of drug testing they're doing. The kind of drug testing they would do, like usually for work, where you're urinating into a cup, that's different. They're looking for chemical signatures within the urine. The hair pull, yeah, they're looking for residues. But like this, mass spectrometers are great when you have solid samples. Can you do mass spectroscopy on liquids? No, liquids usually are tested differently. So, yes, you've done liquids in the mass spec?
Well, I guess it's a GC.
Oh, okay, well, GC is slightly different. Yeah, okay, yeah. That's the, what does GC stand for? Gas chromatography or something like that, where you can take, so chromatography, does anybody know what chroma means? Color, okay, it's the Latin root for color. So what you're doing is you're taking, kind of gasifying it and then burning it and then looking at the colors that come out of it. That's what that machine does. So yeah.
I don't know if I'm wrong with the technical terms.
I'm probably wrong. We need to go get a chemist.
Our mass spec is connected to a GC.
Yeah, okay, so yes, you can train them up too. Okay. Yeah, like one can do the next, yes.
So I was going to ask you, is the picture of the velocity selector, because I took this from the GC, but
I don't know, might be. I don't know. I wouldn't be able to identify a real one if it hit me in the face. I mean, if I looked at the whole instrument, maybe I could suss it out. Yeah. I have helped them fix their machines over there, but that's usually a vacuum problem. Like, I'm really good with vacuum. I did a lot of work in my graduate school with making vacuums work. Not the Hoover, not the Dyson kind. Like I can make better vacuum than outer space vacuum in a chamber. It's one of my specialties. It's not used very often in life, but if you need to make a plasma, I'm your guy. Okay, so Hall effect. Oh, really quickly, Hall effect. This is just sort of I don't know if this is a tangent or something, but it's come up lately at least in the circles I run in, which is mostly gaming and stuff like that. Hall effect joysticks, Hall effect sensors, Hall effect in your controllers, that kind of stuff. The Hall effect comes about because, well, okay, what is the Hall effect? If you take a conductor and you put it in this magnetic field right here, and you run a current along that conductor, we know a current's going to be affected by a magnetic field, right? So we've got current flowing down this conductor, we've got a magnetic field. That means that positive charges should be pushed like this way. And what will negative charges do? They'll go the other way. Now that I've got positive and negative separation across this conductor, we have a voltage, we have an electric field, and thus a potential. That potential can be directly measured. So what the Hall effect allows us to do is measure the potential that is created when a current flows through a magnetic field. So a conductor in a magnetic field, that current will cause positive and negative charges to separate. Across the plates, we measure the potential. So we can directly measure voltage by a conductor in a magnetic field, which means we have a contactless way of changing voltage. We can change the orientation of the conductor in a magnetic field. So a Hall effect sensor is something that doesn't require any physical contact to measure changes in electrical potential. Analog joysticks, analog devices, there's like a physical rubbing of like a variable resistor or something like that or in there. And that rubbing over time can cause degradation. In a Hall effect sensor, you don't have that. You have no rubbing, there's no contact, because you can measure the changes in that sensor without any physical contact, which makes it kind of cool. But the real cool thing about the Hall effect is that it proves to us that the current carriers in conductors are in fact electrons. This is the one place where we cannot cheat and say, oh, positive charge is the thing that flows in the wire. Because the Hall effect, when you look at this from the point of view of, say, positive charges and it does one thing, but if I look at it from the point of view of the electrons, because the electrons are moving the opposite way, they would go a different way. The polarity of this voltage tells us without doubt that it's actually electrons that are moving in conductors. So that's the other claim to fame of the Hall effect. The Hall effect is hard, it's pretty hard. I'm just sort of glossing over some of it here. I remember this very, very well because, so I don't know if you're aware, in graduate school, if you're going into a PhD program, you do 2 years of classes and then you take like an exam. It's like an exam to get your master's degree. If you're getting a master's degree, you don't take the exams because the exams are just there to make sure that you can go on and do PhD work, okay? I was getting a master's degree. I was not planning on getting a doctorate degree. I had already gotten my job here at Fresno City College and I was defending my thesis, right? So defending your thesis takes like a couple hours. You're talking, the people in the room, and they're asking you questions about what you know and your research. My my thesis committee decided, without my knowledge, they never told me this, they surprised me. I was done with my presentation. We had gone over my thesis. They had torn it apart and put it all back together again and blah, 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 blah. They said it was good. And then I said, okay, thank goodness I'm done. And they're like, you're not done. I was like, what do you mean? And they're like, we want to ask you a few questions. I was like, well, you just asked me a bunch of questions. I'm like, no, not about your work. We want to ask you a few questions. And they smiled. Because when a thesis committee says they want to ask you a few questions, what they mean is they want to give you an oral exam. Because part of your exams at the master's level, going on to PhD, you do a written part and you do an oral part. And I said, but I'm not getting my PhD. And they said, we know. And they smiled anyway. They said, we will give you 10 minutes to rest and recoup. And then come back in. So I walked out in the hall where my wife was sitting, nervous, wondering what was going on, right? Okay. And I said, I'm not done. They're like, she's like, you failed? I was like, no. My thesis is okay, but now they want to ask me a bunch of other questions. I don't know what's going to happen. So I walked back in, and they gave me the oral exam. Totally unprepared, right? I had not studied for this. I'd been studying my thesis work, and I'm being asked questions about stuff that's like 4 or 5 years old, right? Like I did this a long time ago. And I was so stressful, and I was so mad, and I was so upset, and I was like, okay, fine. And I'd turn around, and I'd show them, and I'd mess it up, and I'd do this thing. I remember one of those questions was about the Hall effect. And I had been tutoring for 4B, and so I've been helping them in their labs, and finally, something I remember. So I went up here, dumped Hall effect onto the board. And Dr. Allred, he's sitting right there. Can you tell about the post-traumatic stress I'm having right now? He just smiled at me. And it was disconcerting. I was like, Dr. Allred, why are you smiling at me? And he said, because you've done it exactly wrong. I went, you taught me how to do this. You're the one. I came to you and asked you how to do this. Back when I'm your TA. What are you doing to me? And he just started laughing. And he said, you need to understand something. I'm not laughing at you. I'm laughing at me. Because for the last 7 years, I've been teaching it wrong. And now I know just how bad my influence has been. And then he walked up and showed me where I had gotten it wrong, which is just a flip of your hand in the right-hand rule and velocity direction. I will never forget, right, that physicists aren't perfect. We make mistakes. And they ran me through like all my mistakes, everything I couldn't remember, right? And all these different things. And at the end, I was like, why did you do that to me? And they said, we know you can teach. We just wanted to see you teach. I was like, you put me through that? You could have asked me to teach you a lesson. I would have done that. They said, that's essentially what we did. I said, well, did I pass? And they're like, yes. I said, do I get a PhD now? And they said, no. But if you want to apply, you won't have to take your orals. I was like, I'm out. No, I came here. I got a job. I had fun with life. Okay? So you never know when something might come back to get you. And so every single time I see the Hall effect, I go through that. What's that? I mean, if I had gone and done 3 more years of research. Yeah. No. I am not a doctor. I'm better. I'm a master. You may refer to me as Master Balogh from now on. No. One of the things I love to poke fun at Dr. Kerfoot especially, because he's just so fun to poke fun at, is that and he's good. Like Dr. Kerfoot's amazing, but most doctorates I've found tend to lose the ability to speak normally to people. You'll see it. You're going to go on and you're going to transfer to state or other schools, and you'll have a bunch of doctorates that are teaching you. and they are going to be speaking a totally different language. Am I right, Mr. Ragsdale? Okay? Like it's just crazy, right? And it's just, I think what happens is when you get your doctorate, you forget how to talk normal human. Some of you are like, Mr. Bailey, you forgot to talk how to normal human. No, I mean, I only have a master's degree. Only. Jeez. Anyway, what are we doing? What are we doing? Chapter 29. That was the end of chapter 28. We're on to 29. Okay? So, slow reveal here. But we're going to be talking about magnetic fields again. And, where is it? Right there. Okay. I need to show you a video. I need to show you a video about what happens when you send a current through a wire.
We'll use these wire forms and some iron filings to show the shape of the magnetic field around various current-carrying wires. This is a simple straight wire arranged vertically. We'll turn the current on and sprinkle filings around the wire to show the shape of the magnetic field.
So this is iron coming out of that shaker. And it kind of looks like it's going down sort of randomly here. Don't sprinkle iron on your food. They're going to tap. Do you see what happens? Do you see how the iron
Here are two
circulates?
wires carrying currents in opposite directions.
So current up, current down. Do you see what's happening around those wires?
This is a 5-turn loop of wire.
Oh.
Here is a solenoid.
What does that look like? What do those lines look like? Like a bar magnet? Magnetic fields, circulation, circles, closed loops. Those iron filings were getting trapped in something. They were forced into those lines somehow. Why did the iron filings line up? Well, what exists around any current-carrying wire? A magnetic field. So, we are going to spend this chapter figuring out just what the heck is going on with magnetic fields being created by currents. Last chapter, we started talking about bar magnets, permanent magnets. And again, we're going to loop back to those at the very end when we have a little bit of not quite quantum mechanics under our belt. And then we quickly went towards force. We spent more or less all of last chapter talking about the force that charges experience when they are in some sort of external magnetic field. A magnetic field is being applied, charge is moving through, it's going to circulate, it's going to do all these things. Now we're shifting, and the magnetic field we are going to talk about is the one that is created by a moving charge. Where's the moving charge? It's a current, right? A wire with current in it has a bunch of charges moving along. That train of charges gives rise to a magnetic field. Back when we were talking about electric field, we found out what the electric field was for a point charge. Remember that? It was like Coulomb's law, right? Divide by a charge and we get this field thing, right? And the field, bad hair day kind of thing. And then in order to build up beyond just point charges, like to do a line of charge or a ring of charge or a disk, what did we do? We integrated. We integrated. Guess what's coming? What's coming is the Biot-Savart law. Okay? The Biot-Savart law gives us the little chunk of field that we can then integrate to find out what's going on. Back when we did electric fields, remember, like to make the rod, we divided it up into little tiny chunks, right? But I said, right? I said we start with what we're looking for. We're looking for electric field, right? How do we find it? Integrate or add up little tiny contributions. Like we bust the rod up into point charges. We bust the disc up into rings, right? We bust the sphere up into layers of onions or whatever, right? Like it was all about trying to figure out what this little piece of the puzzle was so that we could then finally integrate it. And we ended up with like density functions and lambdas and rho. The horror's coming back, right? Okay. The Biot-Savart law gives us the dB. It gives us the little differential amount of magnetic field that would exist if a current carrying wire could be cut up into little tiny segments. So like here's a wire, right? And we're dividing it up into little tiny chunks, little pieces of like DL here. I'm going to use DS because that's what your book uses, okay? Little tiny chunks of DS. But it's impossible for a little tiny segment of current to exist all by itself. Are we all agreed on that? How do you get a current to flow in a wire? This was the last unit. Voltage, right? You need a battery. You need voltage, right? You need to push those charges along, right? So an isolated segment of current just floating around in space can't happen. It needs to be connected to some battery somewhere, right? So what the Biot-Savart law does is it tells us if a little tiny segment could exist, this mathematically is what it would be like, but make sure that you add up all the segments that connect it back to its source, right? Can't have just isolated currents in the middle of nowhere. So what does this little differential piece of magnetic field look like in the same vein as I want to find this dE to find the whole E? This is what it looks like. Mu naught, which is a new constant. Boy, that was anticlimactic, wasn't it? We're just done for the day. I'm always worried that sometimes that means that the Wi-Fi has gone out. Yeah, those of you that need to go to Clovis can go to Clovis. All right. Good breaking spot for you guys. All right. All right. Mu naught over 4 pi. Mu naught is a new constant. More on that in a bit. Okay. Times the current. Times ds. How are we doing so far? We're good? Crossed into r hat vector. Divided by r squared. That's not a times. That's a cross product. What do you want to tackle first? Mu naught? Okay, mu naught. Mu naught, so back when we did electric fields, we had, remember we had the electric force constant, right? K. Do you remember what K actually was? It's 1 over 4 pi epsilon naught. It's like a shorthand way of being able to write all that junk, right? Okay. And then Q over, right? So the electric field wind is r squared, okay? And you can see here that the Magnetic field is going as r squared too, or also, right? But epsilon naught, I told you epsilon naught, which is the permittivity of free space, okay? It was a dead giveaway. It's the constant that tells you that the electric field is lurking somewhere. It's the constant associated with the strength of the electric field. It sets the strength of the electric field of charges. It's the fundamental constant for the electric field in case epsilon naught in a vacuum. Mu naught is the permeability of free space. So you have permittivity and you have permeability. Permittivity has to do with electric fields. Permeability has to do with magnetic fields. So mu naught is the constant that is associated with the magnetic field. It's the fundamental constant that sets the strength of the magnetic field, again, in our universe, in a vacuum. It is a number, and I don't go weird on me, okay? Okay, just take this number for what it is. We will deal with the implications of this number later, okay? You're used to seeing constants as just big, long strings of numbers, right? This constant has an infinite number of digits. It's 4 pi times 10 to the negative 7. Do I have even written down what the units are? No, I never care. In SI units is what the answer is. Yeah, it's just, I just have it written everywhere in my book as in SI units. What's disturbing here? It's 4 pi. It's like exact, isn't it? It's not like it's, this one was 8.85 times 10 to the minus 12. Something like that, right? Okay. Why what? Fair question. Why don't just cancel out the 4 pi and just give a different symbol? Because mu naught is the fundamental constant that sets the strength of the magnetic field. Like I said, don't go weird on me. Don't read, there's no conspiracy here. Okay? There is an explanation, but we're going to wait on it because you're not ready. You will be. So that's mu naught. 4 pi, you know. What's I? Just the current flowing in the wire. What's ds? It's like the little chunk, right? And it's the thing that, there's two things you really need to figure out when applying the Biot-Savart law. You got to figure out what ds is. So like for a wire that's just stretched along the x-axis, what's ds going to be? dx, right? But if you've got a more complicated, string of wire or something like that, we'd have to figure out like what the x and y components are if we want to do it in Cartesian coordinates. If we're doing it in a circle, maybe polar coordinates, right? We'll get to that. Okay, but the ds is like how you're breaking up your current. Like what shape is your wire? What's r hat? What's r? What are we trying to find? What are we after here? What are we trying to find? Magnetic field. Where? Near a wire, right? Around a wire. The wire, this little segment of current right here, is like a point charge. It produces a magnetic field at some distance r from the thing that's making it. And this is where we're going to pay back all of that preparation I sent you through in the first unit, where I talked about r vector all the time. And I talked about, don't look at r hat, look at r vector. Where does r vector start? on the thing that's causing whatever you're looking for. And where does it end? Where you're looking for it. At any point around this little tiny piece of current, I want to know the magnetic field. Up close, far away, infinitely far away, right up next to it. It varies, but it's the distance from my little tiny piece of current outwards into space. Just like, what's this R in the electric field? It's how far away you are from the charge that's making the field, right? So the Biot-Savart law, the R here is the distance from this little wire segment. We want to find it at that point P. Okay, well, if we want to find it at that point P, I've got to find it from that segment and that segment and that segment and that, right? Don't all of these vectors change? If the shape of the wire changes and the distance from the wire changes for that point that you're trying to find? The answer is yes. And so we've got to be clever and careful about how we set up this integral. But the way we're going to do that is we're going to fall back on this idea. Again, remember, what is r hat? It's r vector divided by its magnitude, right? So we can find r hat and stick it in here. And we'll end up with like an r cubed kind of thing again, right? But generally, it's easier to do cross products with actual vectors instead of unit vectors, although some might argue with me. Anyway, either way, you've got to find r hat. But r vector points from the thing making magnetic field to the thing that's causing magnetic field. I have no idea what's going on here. Because the window is just going away. Crashing. Crash, crash, crash. It got upset at the Biot-Savart law too. Is the fractal pattern calming to you? Unable to connect. Because, did we just lose? I think the Wi-Fi is acting up. I was getting error messages from my email logins telling me that the internet's having trouble. Maybe it's time to go wired. One of the rules that I've decided to live my life by is that computers will always obey me. They don't have any other choice. So the computers that have disobeyed me, they aren't computers anymore. More insight into Mr. Balogh. I was known so I used to work in technical support. I did technical support at BYU. That's how I paid my way through my undergraduate. And we did technical support for like 750 faculty in a College of Family, Home, and Social Science. And I was often tasked with some of the harder problems to solve. I was known as the killer of mice in the office. Yeah. Because I'd be sitting there all quiet, fine, and then all of a sudden a mouse would be impacting the wall. And it was very satisfying because back in the day, all the mice had the balls in them. And so if you threw it just right, you could get the ball to pop out and it would like explode, right? Just like in 3 pieces. And you could pick it up, dust it off, put it back together and keep going. So yeah, I'd be sitting there and all of a sudden I just pick up my mouse and go, and throw it at the back, wall I was sitting next to. And I would get up and walk around, sit down, put it back together and keep going. My boss one day brought in a box of mice and just set it next to my desk. And so I had a box of mice I could just pick up and throw. We had a, I don't know why I'm telling you this story. We had a new secretary come in. We were all working in the same office. It was like open, it wasn't cubicles, it was just sort of open desks everywhere. And we had just met, and nobody had warned her. Nobody had warned her. And so I'm sitting there and I'm trying to figure something out, and I got upset and I picked up this mouse and I just chucked it, right? And screamed, stupid computer. She lost it. First day on the job, can you imagine, right? She just lost it. And I felt so bad, right? Because she's like, what did I do? What did I? It's like, and all the other people in the office are like, what? Oh, this is David. That's what he does, right? And so yeah, she got baptism by fire right there. Anyway, destroyer of mice. Where was I? Oh, technology must obey me. So this law, this equation right here, right, is trying to be a pattern for finding the magnetic field. And we're going to find that magnetic field by integrating this thing. So basically, a magnetic field from a current is going to be found, I take these constants out, by the integral of a cross product. How do you integrate a cross product? Usually you do the cross product first. You try to figure out that cross product first. Get it into a form where you can kind of mathematically deal with it, right? It's a vector. You're going to have another vector come out. There's going to be vector components. Like, that integral looks all innocent, but it really could have three components to it, an x, y, and z, if we're working in Cartesian coordinates. We are going to tackle that on Monday. We're really just kind of getting started with figuring out magnetic fields from currents. Now, before you leave in desperation, okay? The good news is we're really only going to have to do this once. We're going to figure this out once, and what this is going to generate are tools for us to find the magnetic fields of straight wires, curved wires, without having to do this every single time. So if we can get it done once and understand what's going on, that'll make the subsequent equations easier to apply and avoid having to set up this integral every single time. So the first unit, we were setting up integrals all the time, weren't we? This time, we're going to try it once and see if we can't take advantage of that moving forward. So don't despair quite yet. Monday will be rough, but then we'll get through it and we'll be on the other side.